All right, welcome back, students. So this is your fifth week, and so this is your fifth lecture, but we are still going back in the fourth unit. This unit is quite big, so I've broken it up into two parts. Unit A, which was talking about the ionic bonding, and Unit B, the second part, the 4B, is about covalent bonding. Just a little review before we dive into the new material. Last week we talked about ionic bonding. And so remember, ionic bonding is the bonding that occurs between a metal and a non-metal. So iconically here we have sodium as your metal and chlorine as your non-metal. So remember that the driving force for these interactions is that everybody wants to be like the noble gas, meaning it has the full number of electrons on its outermost shell, which is 8, or 2 if it's a first shell, right? So looking in here at sodium, we notice it has only 1 electron on its outermost shell. So once you get rid of that, whereas chlorine has 7 electrons on its outermost shell. So it actually needs 1 more just to obtain the 8th electron. So they both would be a perfect match for each other because one is willing to give electrons, so sodium gives the electron, and then chlorine accepts that electron. So if it does happen like that, then the sodium, as you see here, is now 8 electrons in its outermost shell, and then chlorine also has 8 in its outermost shell. So when that happens, though, that sodium is no longer a regular neutral atom. It is now positively charged. We call that a cation, whereas a chlorine, again, is no longer a neutral chlorine atom. It's negatively charged, so we call that a anion. So it turns out that the positive and the negative particles are very attracted to each other, remember, because opposite will attract one another. And because of that charge of being ions and a negative ion and a positive ion, we call that attraction ionic bond, okay? And remember, the driving force of all of this is that you want to have 8 electrons around your valence shell. So we call that the octet rule. Or if you just have your valence shell as your first, if your valence shell is the first shell, you only need 2 electrons. We call that the duet rule. And we also saw how when this happens, these ions will actually kind of cluster together in a lattice and what we call a crystal structure. So there'll be billions and billions and lots of them all kind of bundled together to form what we see visually in a macro scale as crystals. Right? So keep that in mind as we transition and compare on the other side, the covalent bond, right? So basically everything in the universe is basically ionic bonding or covalent bonding. So these are the two kind of opposites of each other. Of course, there are things in kind of in between too, but they're the two primary groups. All right, so we said we want an octet or duet, and so we can give or take electrons to achieve that. But there is another way we can also share. And we have to do this way when we can't give or take. So for example, we have here, symbolized here are 2 hydrogen atoms, right? So a hydrogen atom has only 1 electron. And so if you have 2 hydrogen atoms, how can they interact? How can they bond, right? So if this hydrogen atom gives its electron to this hydrogen atom, okay, one atom is happy with the duet, but this one is like totally naked, right? So that's not going to work. So instead, they just kind of come close together. If they can't give and take, they can just share. So it's not like one hydrogen atom has 1 electrons anymore, but if they come close enough together, both the electrons are close to both atoms, as if each atom owns 2 electrons. So for example, if you take a look at this guy, within his sphere, he sees there's only 2 electrons, okay, then makes him happy because he has a duet. On the other hand, this hydrogen atom over here sees only 2 electrons in its sphere, so it is also happy with a duet. So because of this, we call these 2 electrons being shared between them. It wasn't given and taken completely, but just shared between 2 atoms. Okay, so we call that the covalent bond. Electrons are shared between 2 atoms to achieve the octet or the duet rule. We can symbolize that with a Lewis dot structure. Remember, we learned how Lewis dot structures can help us symbolize valence electrons more easily. And this is quite useful when it comes to covalent bonding. So for example, here we can represent the hydrogens again with the 1 electron as a single dot. And as you see here, they come closer together so that each hydrogen basically sees 2 dots at the same time. So we can represent these shared electrons in the middle between these hydrogens as a single line instead. So this is a new aspect of Lewis dot structure that we didn't look at last week because there wasn't no covalent bonding. So when there is covalent bonding, we can represent it with a line between atoms. And each line then would represent 2 electrons. Right, so the dashes here represents a pair of electrons, so 2 electrons. And so because of this, we call this molecule a diatomic molecule, di meaning 2 atomic atoms. So 2 atoms come together to make this molecule. I want to emphasize this point as opposed and draw a contrast to the ionic bond, where there are billions and billions of ions just kind of clustered together, in just like we saw previously with the crystal structure of sodium chloride here. In a covalent molecule, when we draw that bond, they don't necessarily have to cluster together. They're individual entities, right? You got a hydrogen, you have the molecular hydrogen molecule, and here you can have it here, you can have it just floating all over the place. They are not bound to each other like they are in ionic bonding. Now, there are other forces that will make these molecules kind of attract to each other and clump together, but we'll talk about that in a later video. But for now, make the distinction that covalent bonds form actual molecules that are its own entity, separate entity, whereas ionic bonding forms just clusters of and lattices of ions. Right, so let's move beyond hydrogen and move something with more electrons. So let's go to fluorine. Fluorine has 7 valence electrons. So again, they're not happy. So if you have 2 fluorine atoms that are both unhappy, maybe one could give its electron to the other, so it makes the one fluorine happy, but the other one has 6. So that's not 8. It's not the same configuration as a noble gas. So only one person happy, the other one's person happy, that's not gonna work, right? It's not like the non-metal and metal case where one likes to give and one likes to receive. In this case, you have 2 non-metals, they both like to receive, so you're not gonna do ionic bonding. So just like in the hydrogen case, if you come closer together, instead of just giving and taking of electrons, you now can share electrons. So you notice we haven't added more electrons to the system, yet both are happy with an octet. If you look at the electrons within the red circle here on the left of fluorine, it has 8 electrons. Now, if you take a close, and if you take count the electrons in the red circle of the right fluorine, it also has 8 electrons. And 2 of those electrons are counted in both cases, right? So those 2 electrons are known as the bonding pair of electrons. And so again, we have represented that with a dash in a Lewis dot structure. And again, we call that dash a bonding pair of electrons. Now, in this case, there are the other leftover electrons. Since they are not involved in the bonding, they are called non-bonding electrons, or called as simply as lone pairs. So in this case, hydrogen, just like hydrogen's case, the 2 fluorine atoms that come together is also called a diatomic molecule. So this is molecular fluorine. It is a gas at room temperature and atmospheric pressure. Now we took first 2 examples of identical atoms, but in actuality, they don't have to be identical atoms to share. Okay, so for example, if you had a hydrogen and a fluorine, 2 atoms that are not yet octet or duet, but both of them don't want to give or take electrons, or both of them want to take electrons, both of them don't want to give electrons, so you can't do ionic bonding. So instead, you come together and you share instead. And so a sharing of 2 electrons will give hydrogen a duet and a fluorine an octet. So you represent that with a dash, a line, a dash line, between hydrogen and fluorine to represent the covalent bond. Okay, now let's move beyond two atoms. We can actually bond with multiple atoms at the same time in a covalent fashion. All right, so for example, take a look at here. We have three atoms this time, one oxygen and two hydrogens. So remember, oxygen has how many valence electrons? Remember how we do that? We take a look at what column it is on. It is on column 16 or 6A, right? Both of those means that they have 6 valence electrons. So it happens that it needs just 2 more electrons to be happy. Well, there's 2 hydrogens around. So each hydrogen will contribute 1 electron, so making that an octet for oxygen, but at the same time making it a duet for the hydrogens. So in this case, the molecule has a central atom, which is oxygen, and that atom is bonded doubly, twice, each to a single hydrogen, right? So two, what we call a single bond. So it makes everybody happy. And this molecule may be very familiar with you, is water, right? It's H2O. We write the subscript 2 in the bottom of hydrogen to note that there are 2 hydrogen atoms. Let's take a look at another example here. We have 1 carbon this time. Remember what carbon, where it is in a column? And how many valence electrons does it have? It would have 4 valence electrons. So it needs 4 more electrons to be an octet, really, right? So it turns out then it will bond with 4 more hydrogens, each hydrogen giving it 1 electron, not giving it, but sharing it 1 electron to make it an octet for carbon and duet again for hydrogen. So again, we can represent this molecule with carbon with 4 bonds, 1 bond to each hydrogen. Does anyone know what this compound is, what this molecule is? You use it in your cooking maybe. If you have a gas stove, it is methane, or the British like to call it methane. Yeah, so CH4, the 4 there, subscript means it has 4 hydrogens for 1 carbon. So again, both of these are molecular or covalent compounds, so they are actual entities. They exist as one molecule, not as an array of them. Yeah, so methane is a covalent compound also. It's the fire that you use if you use a gas stove at home. All right, so how do we draw these Lewis structures? So you would need to you should be able to draw simple Lewis structures in this class, and here are the 4 steps to doing so. First, you have to tally up all the valence electrons you have from each atom. Remember, you cannot draw Lewis structures using electrons that aren't there, or you haven't used all of them. You have to use, so you have to know the exact amount of valence electrons you have from each atom. Number 2, you need to determine which atom is the central atom, and there's some couple rules for this. First is carbon is always going to be your central atom in this class, and hydrogen is always going to be on the outside. It's never going to be the central atom. Now, beyond these 2 elements, then you want to use the atom that is in least amount in the formula to be in the center, right? So for example, if it's NO2, right, there's only 1 nitrogen, so that nitrogen should be in the center. Now, these rules don't work like all the time, but they will be the rules we will use for this class. And the third step is then you just connect each atom to the center atom. Remember, each time you connect, you draw a line, a dash, that represents 2 electrons, okay? And so we want to you do 1 bond first, so a single bond. You want to, I should put a note here that after you connect each atom, if there are leftover electrons, you want to give it on the outside atoms first, and then until it reaches an octet or a duet. Now, when there are no more space to put those electrons, then you want to put them into the central atom. Oops, that's an important part. Okay. So step 4, if after you have done that and an octet is not reached, you might have to consider and draw in double bonds and or triple bonds. Okay, so I will go and give you some examples of these, how to use this rule. And we can summarize this rule. The first rule is basically valence, right? Count all your valence electrons. The second rule is know what is your central atom. A third step is to connect them. And the fourth step is to make sure that everybody's octet and duet, and that you have only used the number of valence electrons that you have, no more and no less. I put this table here just to remind us how to find those valence electrons. Remember, if they're in group 1, or aka 1A, they have 1 valence electron. Group 2, aka 2A, they have 2 valence electrons. But actually, we won't really worry about these two, because covalent bonding only occurs between non-metals. So over here, right? So for example, group 7A, 7 valence electrons, 6A, 6 valence electrons, 5A, 5 valence electrons, so on and so forth. These numbers here, don't worry about them. We will use them in a bit. They are a new idea, so just ignore them for now. Okay, so let's go to the whiteboard here so I can show you how to draw Lewis structures. So our first example is of formaldehyde, which is the molecule they use for preserving things. For example, preserving a corpse in the morgue. Anyways, that's the molecule here known as formaldehyde. It has 1 carbon, 2 hydrogens, and 1 oxygen. So how do we do that? Let's follow the steps here. The first step is to count your valence electrons. So step 1, you have carbon, hydrogens, and oxygen. Remember, carbon is 4 valence electrons because it's in the 4th column. Hydrogen is 1 valence electron because it's in the 1st column, but it has 2 hydrogens, right? So you have to multiply that by 2. So that's a number of total of 2 electrons. Oxygen has 6 valence electrons. So together that is 12 valence electrons. Okay. Step 2, we have to decide what is the central atom. Remember, the first rule was that if it's a carbon, it's going to be your central atom, right? So carbon is central. So everyone else is going to be connected to carbon. So step 3 is to connect them. So we have carbon connected to, let's say we have 2 hydrogens, right? And you can connect them in any way you want to. You don't have to draw hydrogens like this. You can draw hydrogens on the sides. It doesn't matter. And then there was an oxygen, no? Yes. So we have 3 things connected to them. So far, how many electrons have we used? We have used, each bond represents 2 electrons, right? So 3 bonds is 6 electrons. So 12 electrons total, but we have used 6. So we have 6 electrons left. I want to keep a little bookkeeping. Right, so in part of step 3 is whatever valence electrons you have left, you can go ahead and put them on the atoms on the outside first before you dump them into the central atom. So if you have 6 valence electrons left, I'm going to give it all to oxygen, because if we give 6 to oxygen, then it has an octet. Now at this point, we're out of electrons, right? We have used 1, 2, 3, 4, 5, 6 pairs. 6 times 2 is 12 electrons. So we're done. We can't do any more. We can't use more electrons than we have. So in this case, we have to go to step 4. Sometimes we don't have to go to step 4, but sometimes we would. In this case, we do. So step 4 says, if you don't have an octet for every atom or a duet, if it's hydrogen, then you need to share electrons in order to share more of the lone pair electrons to become bonding pairs of electrons in order for everybody to be happy. So notice who's not happy yet. We have oxygen has an octet, hydrogen has a duet, but carbon only has how many electrons? It has 3 bonds, right? So 3 times 2 is 6, right? So I'm gonna use a different color here. So step 4 is I'm gonna take 1 pair of electrons from the outside oxygen and kind of move it inside. If I move it towards the middle here, then it's going to be shared between the carbon and the oxygen. All right, so I'm going to move it. So I'm going to erase that double bond, that lone pair, and draw a dash to represent that it's being shared between carbon and oxygen. Notice when we do that, The carbon has how many electrons now? Carbon has 8 electrons, right? It has 4 bonds connect to it. 4 times 2 is 8. What about oxygen? Oxygen has 2 pairs of non-bonding electrons and 2 pairs of bonding electrons. So that's also 8. So yes, everybody is octet. So this, in fact, is the Lewis structure for formaldehyde. Again, always check, do we have the total valence of electrons correct? And is everyone happy with a duet or an octet? All right, let's do this one more time. Let's do this with carbon dioxide, CO2. So step 1, we say carbon has 4 electrons, oxygen has 6 electrons, but there's 2 of them. So I'm going to multiply the 6 by 2 is 12. So a total of 16 valence electron. I'm going to abbreviate valence with the letter V there. Okay, so what's my center atom? Carbon. Okay, so carbon is in the middle, connected to oxygens. So when I do that, I use how many electrons? 4 electrons. So I have now 12 valence electrons left. Okay, so I'm going to first make sure that all my outside atoms are happy with an octet. So to do that, I give 6 to one oxygen and 6 to the other. That means I have 0 left, right? So I have no more electrons. So it looks like I have to go to step 4 this time again because carbon is not happy. It only has 4 electrons. It needs 8. Just like in the previous case, I'm going to have to look at one carbon over here and one oxygen over here and say, hey, I'm not happy. So can you share that lone pair in? So oxygen says, sure, I'll share in. Right, so go ahead and share it in by drawing our bond that way. Now, you can take another look and see if everyone's happy yet. Is oxygen still happy? Yeah, oxygen still has 8 electrons, right? What about carbon? Is he happy yet? Not quite, because only 6 electrons, right? So it can benefit to get another pair of electrons to reach the 8, the octet. Now it can continue taking away another pair from that oxygen, but nature doesn't like to be lopsided like that. If it's taking too much from one, it's not good. So it looks to the other side. Well, on the other side, there's also an oxygen with a lot of lone pairs. So why don't it ask it from that one instead, right? So it's going to go ahead and say, hey, you have a lone pair here. I'm going to take it and put it in between us, and we can share it. So there we go. Carbon now has 8 electrons. Oxygens all have 8 electrons, and we have a total of 16 valence electrons used. So everybody is happy. So notice then, anytime we draw a bond that has 2 lines to it, we call that a double bond. So sometimes you may have to draw double bonds in order to get the octet. In the other case, in the previous case here, we also had a double bond, but we also had single bonds. So a structure can be a mix. It can have only single bonds, it can have a single and double bond, it can have a single and triple bond, or any combination of that. A triple bond is basically, since we're here, a triple bond is when, for example, you bond 3 times towards something. So maybe in your homework, you might see an example where you might use a triple bond. The one final point I want to talk about before we move on from Lewis structure is that whenever you can draw a structure with single bonds, it is always better than a structure with double or triple bonds. Even though in both cases they follow the rules of octet or duet. Right? So for example, here, oxygen difluoride, notice that the fluorine here has 8 electrons, oxygen has 8 electrons, this fluorine also has 8 electrons. So everybody's pretty happy, right? However, you can also make everybody happy with the octet if you just draw a single bond. Okay, so you don't have to invoke double bond. So don't invoke double bonds or triple bonds unless you really have to. If you don't have to, then a single bond will suffice. All right, so let's move on now to naming. Another big word for naming is nomenclature. So how do you name binary covalent compounds? Binary means it has, and a compound that has only two types of elements in it. So that's why it's called binary. In order to name these compounds, you just add a prefix that lets you know how many atoms of a single element you have in that compound in the front of the element. And you would need to know these prefixes. So the first couple of three you probably have heard before, so it's not new to you. Mono means one, di will stand for two, and tri will be three. Maybe tetra you haven't heard of, but so tetra would be 4 atoms. And then after that, 5 and beyond, they are Latin root words. So hopefully you are somewhat familiar with them in your geometry class. For example, penta is for 5, like the pentagon has 5 sides to it. Hexagon has 6 sides to it. Heptagon also has 7 sides to it, but maybe you didn't know that. So one anecdote that helps students to remember why hepta is 7, even though you can't say septa, but septa is another way of saying hepta in just Latin, is the calendar. What month in the calendar is has the word septa in it? September, right? So is that the 7th month? Well, it used to be the 7th month when the Western calendar only had 10 months. September used to be the 7th month, but they want to add 2 more months in there to make a year fit in terms of the time span. So in order to squeeze 2 more months in there, it was named after 2 kings. And if you are kings, you don't want to be named after winter months, right? So 7th month is very summery month. So guess what is the 7th month? The new name of the 7th month, named after Julius Caesar. So we call it July. And the 8th month, August, is named after King Augustine, right? And then so the former 7th month, September, is now pushed down to all the way to being the 9th month. And you can see the pattern here. Oct is supposed to be 8, right? Like octopus and octagon is 8, but it's supposed to be the 8th month, but it's pushed down from 8th to become 10th now. So it's now the 10th month. Nona, right? What's after 10th? 11, right? So November is the 11th month, even though it's supposed to be 9th. And then lastly, Deca. This one you should know. December used to be the 10th month, but now it's the 12th month. Everything's been shifted down by 2 basically after September. But you also know deca because you know the word decade, right? It's 10 years, so that's the same root word. So hopefully that kind of story kind of helps you remember these prefixes. So let's see how we would use them. So it's very straightforward, much more so than in ionic naming. Covalent naming, you just tell it straightforward. How many of each atoms you have, there's no guessing what the charge is, for example. So for example here, if you have 1 carbon, and if it's something in the front though, you don't say mono, right? If it's 1 carbon, you might say monocarbon, but if it's in the front, you just drop the mono. So if it's 1 carbon, you just say carbon, and it's 4 chlorine atoms. We just also call it chloride, but now with the prefix tetra in front of it. So that's called carbon tetrachloride. Now let's go backwards. If it's something called dinitrogen pentoxide, okay, so the first atom there is nitrogen, and there's 2 of them, right? So there should be 2 nitrogens because of the di. And then the next atom is oxygen. How many oxygens are there? What's the prefix there? Pent, right? So that's 5. So 2 nitrogens and 5 oxygens. So you would write as N subscript 2, O subscript 5, right? Very straightforward in translating them. There are other rules, but I'm not going to be too picky on them. As you just know the basics, you're good enough. All right, so let's talk now a little bit about the fact that we said in the beginning that this Covalent bonding is a sharing of electrons, which is opposite of giving and taking completely. One takes all electrons, the other one just gives its electron. Sharing electrons, though, is not always equal. Okay, so sharing electrons could be equal, but it could be like they're sharing, but one hogs the electrons more than the other partner. So let's start with the equal sharing. If you are the same atom, right, both of them are hydrogen, so they're gonna have this kind of equal affinity or like greediness for the electrons that's being shared. So it's gonna be a very equal sharing, just like when it's two fluorine atoms. So when it's being shared equally like this, we call it a non-polar bond. Um, non-polar, right? And so let's say why is it called non-polar? Let's look at what is a polar bond then. So for example, here it turns out oxygen and hydrogen is a very polar bond. It turns out oxygen wants and hogs the electrons much more than hydrogen. So even though they're sharing, it's holding on to electrons closer to itself than is hydrogen. So because of that, one side is more electrons are more negative than the other side. The hydrogen is more positive. So there's a difference in a large difference in that bond. So there's a polarity. It's a pole, right? So we call that a polar bond. So the opposite of a polar bond, then it's a non-polar bond where there are no poles. There's no positive and negative. And this one is there is going to be positive and negative. The electrons are being pulled towards oxygen more, so it's more negative. Hydrogen is lacking the electrons, so it's more positive. Now, just because you're a different atom doesn't mean you're going to have a polar bond. So how do we dictate polar bonds? So that brings me to that table that I shared earlier. There's this number in the bottom here, and you can use this table, and I'll provide this table on a test, for example. If you take a difference between these numbers called an electronegativity value, which is basically their greediness or their wanting of electrons, the higher it is, the more electronegative, the more greedy they are to electrons. If the difference is 0.4 or below, right? If the difference is 0, let's say, for example, if two hydrogens are bonding with each other, it's 0, right? 2.1 minus 2.1 is 0. Therefore, it's nonpolar. So if the difference is from 0 to 0.4, you are considered nonpolar. Greater than 0.4, you're considered polar. Okay, so let's look at this example here. Oxygen, which is 3.5, hydrogen is 2.1. The difference is what? 1.4, right? So that's why oxygen and hydrogen bonds are considered polar. What about carbon and hydrogen bonds? Carbon is 2.5, hydrogen is 2.1, so the difference is 0.4. So that's the cutoff for being non-polar. So that's why this is a non-polar bond. All bonds here are non-polar. Both of these bonds are polar. All right, so now the next concept is if you have polar bonds and non-polar bonds, you can then lead into the molecule being polar or non-polar. So the first case is if you have non-polar bonds only, then the whole molecule is considered a non-polar molecule. So that whole molecule, there's no positive or negative ends. For example, these two, right? And then these two, and then this molecule too, methane, has only non-polar bonds, so the entire molecule is considered non-polar molecule. Oxygen has a polar bond, and because of its geometry, the whole molecule is considered polar molecule because it pulls its electrons all the way towards the oxygen, so much so that on this end of the molecule, there aren't that many electrons, that the oxygen pulls electrons to one side, leaving one side pretty positive. So the whole molecule is considered a gigantic pole with a positive and negative end. So the whole molecule is polar. Now in this class, you don't have to be able to determine what is a polar bond, what is a polar molecule or not, because in order to do that, you would need to know about geometry of the molecule, and that's too much for this class. You do need to know polar bonds, but polar molecules you do not need. But so because of that, I will just tell you if a molecule is polar or non-polar. So if I tell you that, what can you do with it? So this comes to this concept of like dissolving like. So polar molecules will dissolve in other polar molecules. Non-polar molecules will dissolve only in non-polar molecules. So if you mix them, they will not dissolve each other. So let's look at two examples, two primary examples of that case. Think of vodka or any kind of alcohol you have at home, or even like in your in rubbing alcohol when you disinfect. In that bottle is a homogeneous mixture. Remember that word, homogeneous? So it's a mixture of two compounds, but you can't see them apart. That's why it's called homogeneous. And why is that? It's because you have water, H2O, and then ethanol, the alcohol. These two molecules turn out to be both polar molecules. So they dissolve in each other very well. So well that you can't tell them apart. So if you look at here, you can't see the water apart from the ethanol. Okay, so because they're both polar molecules. Now, if you take that water though, and you then want to add with oil, what happens? Oil is just like the methane we saw earlier. It's a bunch of carbon and carbon bonds and carbon and hydrogen bonds. Both of those bonds are non-polar, so the overall molecule is non-polar. So non-polar molecule will not mix with polar molecule. You maybe have seen this when you make a salad dressing or when you buy salad dressing. What do you have to do with it before you use it? You have to shake it well, right? Why is that? Well, because remember, you add in your vinegar, which is water-based, and then you add in your oil, which is oil-based, and they're opposite of each other. So they won't dissolve in each other. So when you make it, you have to shake it well for them to kind of mix, right? And you have to like use them immediately. If you just let it sit there, minutes later, hours later, days later, they will just again go into the individual compartments, right? So the oil layer will separate away from the oil layer. That's why you have to shake it well before you use it again. Okay, so that illustrates the idea of like dissolving like. And again, I will never ask you to determine if a molecule is polar or non-polar. I will tell you, and then you would have to apply this rule to it. All right, so let's take a step back and see where covalent molecules exist in our everyday life. Beginning of this lecture, I told you there are two types of bonding. One is ionic bonding, we covered last week. And so everything else in nature will then be covalent bonds. Okay, so iconically here, CO2 is the covalent molecule that plants take in order to do photosynthesis, and then they will release another covalent molecule known as O2, molecular oxygen. And we just talked about this too. Ethanol is the primary ingredient to get you tipsy or drunk when you drink your alcohol. So it is full of covalent bonds, that CH bond, that CC bond, that CO bond, and that OH bond. So many, many different types of covalent bonds in ethanol. And we get even bigger molecules here in drugs. Basically, for the most part, I can't think of any, but I think all the drugs that you can think of are molecular drugs, unless they're like biological drugs that are basically also just big molecules. Like for example, here we have here is Tylenol, which has a bunch of carbon bonds, a single bond, and carbon-carbon double bonds, and carbon oxygen bond, carbon hydrogen bond. So lots of covalent bonds in there too. So we're gonna not talk too much about these molecules known as organic compounds because it has a carbon in it. We're gonna have a whole separate unit on talking about these molecules. So in this unit, there's a subset of covalent molecules that I do want to take a look at before we end the lecture, and that is acids and bases. So in everyday life, you have encountered acids before. For example, in your kitchen, you may have used vinegar. Like we said earlier, to make salad dressing, you might need vinegar. Well, the main ingredient in vinegar for the taste of vinegar is this compound called acetic acid. Okay, so that is one example of an acid you may know. On the other hand, we have bases you may know. In your cleaning product at home, you may encounter ammonia. When you put these molecules in water, there's something that's special that happens to it that qualifies it as an acid and a base. When an acid is put in water, so for example, acetic acid, when it is put in water, it loses a proton. What is a proton? A proton is a hydrogen atom that is positively charged. So it has no electrons, right? So we call that a proton. So when it loses that acidic or protic acid, or acidic or protic hydrogen, we can call that an acid. On the flip hand side, when a base is put in water, what happens is that usually a base will have a lone pair, and that lone pair will then attach itself to one of the hydrogens in water and taking it away, leaving behind this moiety, this group here, H and oxygen. Remember what H and oxygen together was called as a polyatomic? Is a hydroxide, right? And which is a negatively charged anion. So that's the definition of a base. Anytime you put into water and it produces OH minus, we call that a base. Anytime you put in water and it produces an H plus, we call that an acid. And there's a wide a range of being acid and base. You can be a strong acid or a weak acid. You can be a strong base or weak base, and you can compare that on this scale here. You may have seen this scale before in your life, and the scale is from 0 to 14. And on the scale, on the left-hand side, we call that acid, and on the right-hand side, we call that base. Okay, so let's start on the far end of the basic spectrum here. At the far end, at pH, and it's called pH, it's called a pH scale, by the way. So if you have a pH of 14, that's a very, very strong base. That means if you put that in water, you will produce a lot of OH, a lot of hydroxide ion. So for example, lye, which is the what you use in your drain cleaner, for example. And it's very, very caustic, so you may get burned if you just have long exposure to the substance, for example. Another word for basic here you can see is alkaline. And you may have seen this word a lot when they advertise to you about like alkaline water being healthier for you, which there's no real evidence for, but people will believe that and they buy more expensive water just because it has higher pH, it would be called alkaline water. In any case, we're not going to discuss the validity of those statements. Just want you to be aware and connect the dots here. Now, if you move down from 14, you go into more neutral regions or less severe regions, I should say, not neutral quite yet. For example, if you move on to pH 10, you will see your laundry detergent. pH 9, you will see your soap. Okay, and then as you move more into the 6, 7, 8 region, this is more of the neutral region. For example, if you are perfectly at 7, you're perfectly neutral. But you don't have to be perfectly then at 7, but you can still be between 6 and 8 to be considered quite neutral. For example, blood is in there. And there's two figures here that says ocean water. It used to be more basic, it turns out. In 1870, it was 8.18, and it's projected in 2100 to be much more acidic at 7.76, actually. And so this acidification of the ocean is because of the pollution that we put into the atmosphere from burning fossil fuels. So CO2, when it's in the atmosphere, it can be incorporated into ocean, making it into carbonic acid, making the ocean more acidic. And that contributes to, have you heard of something like coral reef bleaching, right? So basically the coral reefs are dying because the coral reefs can't incorporate the carbon, the calcium in order to grow because the pH level is not perfect for it to do so. pH is actually very important. The balance of it is very important. Just a slight change will be dramatic. For example, in our body, we have a pretty neutral, we have a pretty balanced pH, and if you just slightly go off on one end, it would indicate illness or it can cause illness. Yeah, so we'll take maybe a closer look at that another time. So now if we go beyond here, we go to the acidic region. For example, anytime you have fruit, there's a lot of acid in fruit, or even fruit water like wine has a pH of 4. Cola, there's no fruit in cola, but it has phosphoric acid, which is put in there for to preserve it, and also for flavor. Because remember, um, acidic, I'll talk a little bit, has a little bit of a sour taste, so it's good. So phosphoric acid is in there, so it has a pH of 3. And you go to the very end here, you get hydrochloric acid. This is very strong acid. This is your stomach acid. It makes sense for your stomach to have a very strong acid, right? Because you want to be able to break down all the food that you ingest in order to make them into energy. In order to break down the food, you need something that's very, very reactive. So you have hydrochloric acid in your stomach. All right, so that's the pH scale. Let's go and talk a little bit about the properties of acid versus bases. So my primary example here is lemon, because lemon is very citric acid. Like I said, fruits have a lot of acid, so lemon is one of them. And we saw previously that it has a pH less than 7, but even though I said 6 to 8 it's considered neutral, but like by definition, if it's less than 7, it's considered acidic. And again, we said it tends to have a sour taste. Citric acid, acetic acid and vinegar, very sour taste. And it turns litmus paper red. Okay, so if you have a litmus paper that's blue and you dip it into acid, it will turn into red. And I'll talk about litmus paper in a bit when we talk about base also. But for now, let's just keep in mind that it does turn litmus paper red. And lastly, the last property I want you to realize is that it is also an electrolyte. What is an electrolyte? An electrolyte is something that can carry electrical current in water or in a solution. And it's electrolyte, why? Remember, because it releases an H+. Because of that ion that's being released, the ion can carry a electrical charge. Okay, now let's compare that to base. And our primary example base, like I said earlier, was ammonia. So pH is more than 7. The taste of base, not as great, so you don't put it in your food as much. So it has a bitter taste. It has even a slippery feel to the touch, and it turns litmus paper blue. If you dip red litmus paper into a solution, it would turn it into a blue color or violet color. That would tell you, okay, I have a basic condition, a solution. That tells you I have a basic solution. So this is used beyond chemistry and in your everyday life. This terminology has been come to use. For example, people say this is a litmus test for something. It tells you that the results is either one way or the other, right? So that's how you can see the word litmus test. Because in chemistry, it can either tell you of two things, right? One of two things. It could be acidic or it could be basic. That's what litmus paper can do. It's very binary. And then lastly, just like acid, bases can also be electrolytes. Why? Remember, it releases an hydroxide ion. So anytime it has an ion, it can carry electrical charge. All right, so let's take a look at some common acids. And we won't talk about them too much because throughout this lecture, I have also kind of touched on them a little bit already. So for example, here we have hydrochloric acid, HCl. Remember, that was your stomach acid. Nitric acid, we haven't talked about this one, but its formula is HNO3, and that is used in like fertilizers and in chemical bombs, for example. Sulfuric acid, H2SO4, it's used in batteries, but also like nitric acid, it is for fertilizers and also weapons. Phosphoric acid, H3PO4, we talked about this one. This is the one that's in your cola. It's there to preserve as a preservative. And then acetic acid, we talked about this. This is the vinegar, the acidic acid, HCH3CO2. And lastly, carbonic acid, H2CO3. I kind of mentioned this when I talk about ocean acidification. That's the carbon dioxide that goes into the ocean water. It turns itself into carbonic acid. But that's also a substance that's put into your soda pop to make it bubbly, right? You put carbon dioxide in there, or carbonic acid, to make it bubbly when you drink soda. A few things I want to point out. Most of the times when an acid is written in its formula, the acidic proton, the proton that is released, is written in the front of the formula. You see all the hydrogens here? It's all in the front. Now, some acid has only one hydrogen, some has 2 or 3. If it has only one, it's called monoprotic acid. 2 is diprotic. 3 is triprotic. And then the number corresponds to the charge of the anion. For example, Cl has a -1 charge, so there's only one hydrogen. Remember, hydrogen is +1, so that's charge balance. NO3 is -1, so 1 hydrogen. SO4, remember sulfate is 2-, that's why 2 hydrogens. Phosphate as a polyatomic is 3-, so it has 3 hydrogens. All right, and lastly here, we want to end with talking about some common bases. I talked about sodium hydroxide already, NaOH, that's in your lye. Magnesium hydroxide, MgOH, parentheses 2 there, is antacids or laxative. Depends on the dosage that you take. And then ammonium hydroxide, we talked about, is basically the ammonia. NH4OH there is your household cleaner or fertilizer. Notice that all of these are going to be ionic compounds, really. So when they are solids, you add them into water, they will break up into their ionic components, their cation, and then their anion, which is why they are a base, because their anion release is the hydroxide anion. Okay, I think that will be it for this week's lesson. This chapter, again, is pretty big and pretty tough to handle if you don't take your time with it. So take small bites at a time to kind of understand this unit, unit 4. So last week, again, we covered 4A, ionic. This week is 4B, we covered covalent.